Welcome to the last day of our workshop on AI. So today, to give you a brief introduction of what we have discussed yesterday, we started with Perceptron and we built a Perceptron right from the scratch. We built every component of the Perceptron, like uh, propagation, forward propagation, and then optimization, backward propagation, put it into a loop. We iterated for 200 iterations, and that is on only um, one single perceptron. But in general, whenever we try to build neural network based models, we don't use a single perceptron. We actually use a multi-layer perceptron where we would have many neurons connected in the form of a network, in the form of a graph. Now, if we have to build such a complex network of neurons, how can we do it? We can do that with just like how we built one single perceptron, but the amount of um, coding that we have to do and finding out those derivatives and trying to back propagate them will become too complex and too clumsy. So this is where we would take help of the frameworks like, let's say, Keras, um, TensorFlow, and then PyTorch. So for today, I would show a simple example on how we can build such a complex network with the help of a Keras. The other day, I think on the second day, we saw an example for ML. We tried to build a churn model with trying to predict the target variable churn using all the rest of the input variables, right? Now, let's use the same data and try to build a multi-layer perceptron and see how it performs and how we can optimize this multi-layer perceptron better. Compare it against with what we have done with the help of a decision tree. We trained that model with the help of a decision tree before. For the same data, I'm going to show you how we can train to train a multi-layer perceptron to come up with the same predictions. So the inputs, if you remember that data, we have around 17 variables as inputs. So that's like all the way up to 17, x1, x2, so on, all the way up to x17. And I am going to build a hidden layer. So this is my H1. And I can decide the number of neurons in the hidden layer. General concept is at the first hidden layer, we would go with the same number of neurons as we have the number of inputs. So we have 17 inputs. So I am placing 17 neurons here in the first hidden layer, H1 layer. By default, the network architecture that we are going to choose for this MLP is a fully connected network. So what fully connected network means? Every neuron should get connected to every neuron, either input or output in their immediate layers. Okay, so let's look at this. Here we have 17 inputs, right? So each of these 17 inputs should get connected to each and every neuron. So like this. So input 1 is connected to all the 17 neurons in the hidden layer. And second input should be the same, should be connected to each and every neuron in the next layer. So we will do this for all the neurons that we have in this input layer. Okay, so here we need to initialize 17 by 17 weights. So this is going to be a matrix which has 17 by 17 weights. For example, W11, W12, W117. And similarly, W21, W22, all the way up to W217. Okay. This is my hidden layer. And it is our responsibility to decide the network, how our network is going to be. Like, for example, if I have to add one more hidden layer, let's say I want to go with another hidden layer H2, I can add that hidden layer. But for now, I am not going to add one more hidden layer. I will directly generate a output from this. So from here to here, every neuron of the previous layer should get connected to every neuron on the next layer. So that's what a fully connected layer means. Now, the natural question that you may have is it mandatory to connect every neuron in its previous layer with every neuron in its next layer? No, not mandatory. But to start with, we always go with a fully connected network layer. So that's why in this network architecture, we are going to see a fully connected network. Later, if a fully connected layer is not really doing a great job for us, we can try to decide and drop off some of those connections. We will see all these things when we actually do the example in Python. You cannot exactly decide which connection to drop. For example, you cannot say, I will drop the connection from the input X1 to the 17th neuron. So you cannot mention like that. Why we cannot mention like that? Imagine when you give images as input. Now your image could be a 4000 by 4000 image. So that's like 4000 by 4000 pixels. So the 4000 by 4000 would almost result into a kind of like billion weights there. Now you cannot decide which weights to be dropped, which weights has to be proceeded forward manually. So that's why we can simply mention, let's drop some of them. It decides which of them can be dropped. So that's why I'm not going to touch that part. We would in this example we would go with a fully connected layer itself, right? And then in your output layer, generally your output layer is decided by your target. So in my target here, I am going to build a binary classification. So I am going to have by default 2 neurons over here. Next, the next thing that we need to decide is what is the activation function at each layer. You cannot decide the activation function of each neuron. That would be too difficult. For example, if you say, I want to use an activation function of sigmoid here, and I want to use the activation function of ReLU here, then you, then this becomes even more complex, right? Then you have to manually build this complete architecture by yourself. Instead, we will decide the activation function by layer. For example, in H1, in my first hidden layer, I am going to use my activation function as ReLU. So all the neurons in this first hidden layer, my activation function is going to be ReLU. That's what I'm going to use. And here in this output layer, whatever the neurons that are there in the output layers, since my output is, my expected output is a binary classification, by default, I would prefer to go with a sigmoid. If I have multi-class classification, I would have preferred to go with softmax. Okay. Now, what decisions that we have made? We have made these decisions. How many hidden layers? So these are all the decisions as a developer we have to make, right? So we have decided as one. How many neurons in hidden layer? If we have if we have decided to go with more hidden layers, then we have to decide the number of neurons in each hidden layer. So we have decided that as 17. What is the activation function that we are going to use by layer? So what are the activation functions that we are going to use? In the hidden layer H1, activation function is ReLU. In the output layer O, I would use the activation function as sigmoid. Okay. So these are the decisions that we have made. And these decisions are called as hyperparameters. Why these are called as hyperparameters? Right now, I started with this, but it is not guaranteed that I would get the desired output with this network. I will have to do a lot of iterations to figure out what is the ideal network that will give me the best desired output, right? So to start with, we are going with only one hidden layers, but then maybe let's say if we realize that, hey, one hidden layer is not good enough for us to learn, then we need to increase the complexity of our network. So then we would increase our hidden layers. So increase the number of hidden layers. What happens when we try to increase the hidden layers? Let's say, for example, previously, so this is your input space X1 and X2. We have observations like this, and we are trying to do binary classification, right? So these are our observations. There is a huge overlap of the black and red observations. So we are trying to separate them, let's say, with a line. And this line is not really separating them well. So when we, instead of using one hidden layer, when we increase the complexity of our network with an additional hidden layer, maybe now we are trying to look for a non-linear space, that blue line, right? So increasing the complexity means increasing the non-linearity of your model. If the linear separation is not able to do a good job, then we will look for non-linear boundaries of separation. And how that happens is by increasing the complexity of your neural network. Then we would look at the number of neurons. So if the number of neurons is 17 in our first layer, can I increase them or can I decrease them? So in the first hidden layer, we will keep this as it is 17. In the next hidden layer, maybe we will start with half of it, like 8, or maybe we will reduce that even further to 6 or increase that to 10 and see where it works well, where our network is able to generate the desired output from our input. So this is called as hyperparameter tuning. So we need to find out the ideal values of the hyperparameters through which our network will be able to produce the desired output from the input. Okay, so this process is what we call as learning process or the training process. And what are we learning for here? We are actually learning for these weight matrices. And of course, there will be a bias term in each layer. So each neuron will be connected with the bias term over here. And let's call this as B1 and this is B2 and this will be connected to this one. So we would also learn for these bias values and then the weights. Here, how many weights would be there? 17 by 2. So we need to learn these weights and that is what we are calling it as the training process. And one more thing that we need to remember here is how many iterations we are going to train. We will also decide this, right? So these iterations is called as the epochs. So we call them as epochs in the terminology. So how many epochs are required to complete this training? Let's say now we would decide that we would go with the 200 epochs. And this is also a hyperparameter. Sometimes, depending upon your network architecture, we might get to see results within the first 100 epochs. Maybe sometimes we might have to go even up to 1000 epochs. So we also need to find out this hyperparameter. Okay, fine. Now let's see how we can build this network and use these parameters to train a model in Keras. So to understand how Keras work, first we have to understand some of the concepts of the Keras. Okay, the reason why it is called as deep learning, the reason the name deep learning refers to, we are going to use very deep neural networks to learn the parameters. So we would be having a lot of hidden layers. So that's nothing but the depth of your network. So deep neural networks simply means that our network is going to be complex with many hidden layers in it. Okay. So whenever we try to train this deep neural network, Keras helps us in simplifying that process. So let's see how it simplifies that process. So all deep learning networks are sequential in nature. So first thing, we have to initialize our Keras session with this sequential. Then we add layers. What type of layers is decided by what type of network that we are choosing. This network is called as a fully connected network or a dense network. The other name for this is called as the fully connected network or the dense network. The other type of architecture, if you remember yesterday, I spoke about whenever we are trying to train something on images, we would use another architecture. Instead of using this fully connected network, we will use another architecture called as convolution neural network. So we would call this as CONV, C-O-N-V. Con one dimensional, con two dimensional, con three dimensional, so on, right? So if we are using some other architecture, then we would build our architecture using what type of layers that we want to build onto your network. Here, because we are building a fully connected neural network, I am going to add my dense layers. What type of layers that we are going to add? We are going to add dense layers. So we need a dense layer, one layer for each, one dense layer for each hidden layers. So how many hidden layers we have here?
Sir? Hello? Sagar sir. Hello? Maybe Sagar sir got disconnected. All of you please wait for 1 more minute. Sir will join again.
Using the Keras architecture. So all the deep learning modules are sequential in nature. What sequential means? Every fully connected. So every layer is connected with every neuron in its previous layer and its next layer, either it is inputs or outputs. Okay, so that's why we initialize the Keras architecture using the sequential, add layers on top of it. What type of layers that we add? The dense layers. Now, depending upon what architecture that we are going to use, we will have to decide the layers. So for example, here, because we are going with a fully connected layer, we are initializing dense layers. If you are going with convolution neural network, CNN architecture, then we would use layers like convolution 1D, convolution 2D, and convolution 3D. So the layers that we are going to add to our network is decided by the architecture itself. So here we would be adding what we call as the dense layers. Okay. Then what should be the details that we need to give in the dense layers? Okay, adding a dense layer is fine, but we need to mention the details, right? So in the dense, we need to add like how many dense layers that we want. For each hidden layer in your network, let's say if you have 3 hidden layers, we need to add 3 dense layers. And for each dense layer, how many neurons are there in each layer? So that we need to mention. Especially if the dense layer is the first dense layer, that means the first hidden layer, it is connected to inputs, right? So we need to mention how many inputs are there so that as many weights are initialized. So if you have 10 inputs and here you have 10 neurons, it would initialize a weight matrix of 10 by 10. So if you have 10 inputs and you add 20 neurons, possible. Sometimes we will make those architectures also. These are slightly more complex. Now it would make 10 by 20. So especially for the first dense layer, which is directly connected to your input layers, we need to mention how many inputs are there. So it would initiate those many connections. And for the next layers, here it is straightforward, right? Because this layer is coming after this layer. So Keras already know the details of this layer. And in a fully connected network, it has to connect all the neurons of these two layers. So it would automatically figure out that weights for you. Okay. So we need to add how many neurons in each dense layer. This is one thing. If first hidden layer, then we need to mention how many inputs. So these are some things that we have to give. Next, once like this, we will build our network. Once we have built our network, we need to compile it. So we need to compile our network. So the steps are sequential. This is the initialization of your network. Add layers, add dot dense, add dot dense. So this is how you would try to add layers. Then once you are complete with your layers, then you need to compile it. So compile is like making your network flow ready. Then comes your training. Let's say we call this Keras network as NN. Now NN.fit in Python, anytime when we are training something, we use this function fit, right? So NN.fit, here you need to pass your X, your inputs, and then along with X, you need to pass Y, your output, desired output, and some other optional parameters, right? So you need to remember this logic, and this is what is going to help us in building the program. Okay, sequential first, and we will call this sequential as, let's say, NN, and for this is the initialization of your network. Then we complete the architecture of your network by adding dense layer, and within these details in dense, we will add the details of each of these layers, like how many neurons are there, whether it is connected directly to input layer, if it is directly connected to input layer, how many inputs are there. So all those things will go into this statement. Now, finally, once you are done with this, let's say we will compile this. So this will keep our network architecture ready. Now to this network architecture, we are passing our input data. So that is X, and expected output Y. So here is the training process. So here is the learning process. So in this step, it will try to learn how, what is the weights of each of these unknowns and how many iterations. We need to also mention how many iterations we are going to train this. Okay, yeah, it might look little weird here, because you are hearing about Keras and how Keras works and what are these things for the very first time. But just you practice it more and more, you would get comfortable with this. Now let me show that example. We will build those things right from the scratch. If you see here, these are the two things that we are going to. Even this one is also not essential, because I am not going to use the data sets which is built in Keras. We are going to use our own data set, which is this data set. So we need this one. From tensorflow.keras.models, import sequential. When we built our decision tree, you have seen a very similar statement, right? From sklearn.tree, import decision tree classifier. So this is the help given by the Jupyter Lab. So whenever we are writing programs, it is difficult for us to remember all these function names exactly and try to remember the module names and the submodule names. So the moment we type a couple of characters, so from sklearn.tree, import DE, capital DE, and then I hit the tab button. So when I hit the tab button, the auto completer of the program kicks in and it says, hey, there are two functions which starts with capital D and small e. So these two functions, decision tree classifier and decision tree regressor, which one you want to use? So I want to use decision tree classifier. So that way we do not have to remember a lot of these programming by ourselves. So whenever you use these interactive IDEs, which we call as the interactive development environments, they help you in coding as well. So these are some of the common modules like pandas, numpy, matplotlib. We generally use them in many places. So whenever we start writing the program, after the first initial section, which talks about what this program is all about, why we are writing this, then in the first programming section, we will start with importing all the modules that are required for the program. And here we would automatically start with import numpy as np pandas as speed, because whether we use it or not, these are very common libraries that helps us in a lot of data manipulation. So we would naturally go ahead and type them. Then you think about what modules are required exclusively for the program that we are actually building here. So here I am trying to build a neural network and I'm going to train that using Keras. So that's why I need this one. From tensorflow.keras.models, import sequential. So as I said, Keras is a wrapper built on top of TensorFlow. Behind the scenes, it still uses TensorFlow, but it makes our life easier, especially for beginners. Keras workflow is so smooth and so easy than TensorFlow. That's why naturally we advise them to start with Keras than starting directly with the TensorFlow. Okay, so here we would use the Keras module sequential to build our network. This one here is optional. Don't worry about this. This is like setting up how the execution happens. When we install TensorFlow, we have two versions of TensorFlow. One is the CPU-based version, and the other one is the GPU-based version. The only difference is when you run this Keras program at the end, whether it is going to use CPU to do all the computations or is it going to use GPU to use all the computations, right? So it has been proven that GPUs are many times faster in training neural networks than the CPUs. So if you have a GPU in your machine and you have configured that GPU, configuring GPU is like a slightly tough job, right? I would not advise that for beginners. You don't have to worry about how to configure GPU executions for TensorFlow and all. But if we have done that, then this statement tells that, okay, whenever a TensorFlow or whenever a Keras module has been submitted for execution, execute it on GPU, don't execute it on CPU. So that's why this is an optional step, so don't worry about it. I have configured GPU execution on my machine, this machine, so I'm going to go with it. The only difference between a CPU execution and a GPU execution is CPU execution would be slower, at least 10 times slower than your GPU execution. Neural networks takes a lot of time to learn. Sometimes we might train a neural network for 4 or 5 hours also. I have trained even for 24 hours also, right? So when execution times goes into 24 hours, 10 hours, even 1 hour decrease is a significant thing, right? So that's why we would configure GPUs so that it trains faster than the CPUs. Now let's jump into the data. We are already familiar with this data, so that's why I choose this one. I could have chosen something like a image data set or whatever it is, but that would not make much of a difference. And to explain that data set, I would need more time. And because today is being the last day, I do not want to spend a lot of time in explaining the data set itself. Rather, I want to focus my complete energy on how to build the network, how to train the network. So let's do with this. And in this data set, we have these columns, which we are already familiar with. Churn, this is my target column. You can see here, this is my target column. This is the desired output that we have to generate from all these other variables. The all other variables are going to act as my input variables, and this is going to act as my target variable. But knowing this data set a little bit, I know these three variables, state, area code, phone number, are not useful in training. So we are going to drop these three columns. So I have dropped those three columns. So once we drop these three columns, what we have is a smaller data set now, chrn.shape. You can look at the shape. There are 3,333 observations, rows, and 18 columns. Out of the 18 columns, one column is my target column. So this churn column is my target column. So rest all of them are going to act as my input columns. So that's why in my network architecture, I designed a network in such a way that there are 17 input variables, and in the first hidden layer, there are 17 neurons. So these input variables are connected to the 17 neurons in the first hidden layer. And we only have one hidden layer, and from that layer, we will directly generate an output layer. Separating my target column is CHURN. So I'm separating it so that I have all inputs in CHRN. So that is going to act as my X now, input variables. And Y is this column alone, my output column, and that is going to be named as target. So that's what this particular step does. This is a routine thing that we always do. That's why I said the knowledge of machine learning is very important if you have to be a AI developer. Whenever we are trying to train something, we have the two-step process, actually three-step process: training, validation, and testing. So we train any model. Here it is a neural network. In other case, this could be a decision tree. In other case, this could be some other algorithm. So we are going to train with some input data, and we will validate it on a small data set. Validation is like, is it really good? Is the results satisfactory for us? So that's what we call as the validation data set. And to make sure that it gives good predictions, we will use the test data set. So this machine learning is always a three-layer process. Because we are not actually going to use this model in a live production environment, I am bypassing that validation process. So I am only having a training and the test set. Otherwise, we will create three sets: one for training, one for validation, and one for testing. But we would not have the validation part here. We would simply use the test part. So see here, this is X, this is Y, and we are splitting both X and Y into four subsets. That is X inputs of training, X inputs for testing, Y inputs for training, and Y for testing. So that's the four objects that we have created here. What the other important step, I think, which I forgot to mention right now, after looking at the code, I'm able to recollect it. For certain algorithms, including neural networks, whenever we are trying to train, the inputs has to be scaled. So what is scaled? Scaling means bringing the range of your input variables to a smaller range. So there are different types of scaling called standard scaling, which is coming from statistical concept called as z-score scaling. The other scaling is called as the min-max scaling. So let me just give you what min-max scaling is so that it would be quick and people understand. So let's say we have age of the customer. Age is starting from 22 going all the way up to, let's say, 88. So that's the age of all of our customers. When we do this min max transformation on this column age, the new column age will have values between 0 and 1. 88 is going to take 1. Maximum value is 88, so it is going to take 1. 22 is going to take 0, and rest of all of them, let's say we have something like 40 here, which might take it as like a 0.46 or something, right? So all the values are scaled to a smaller range. Here, look at the range. The range is 22 to 88. Here, the range is 0 to 1. Not only this variable, every input variable that we have, be it age, be it the bill amount. Bill amount might be in hundreds, right? So every variable should be brought down to this low scale of 0 to 1. Why it is essential, I will talk about it in the context of neural networks, right? So in the neural networks, all these weights and all these numbers that we are going to deal with are very smaller ones. If we use a very large numbers, they will hit this problem of gradient descent. So the gradient descents are so large so that your fluctuations, whenever you are trying to change the weights, the variation in the weights would become very significant. We do not want that to happen. So all the numbers that are happening, whatever the processing that is happening inside that network, we need to keep them to very small magnitude so that the gradients are small and our changes to the weights are also small. So to keep those gradients small, we have to scale this. Once we scale all these input variables, not a big deal. The entire data that is flowing inside in your network are very small in number, so your gradients will also be naturally small. Not just only for neural networks, and we do this for a lot of other algorithms, other techniques also. So that's what I am doing here. From sklearn.preprocessing import standard scalar. If I'm using a standard scalar, which is called as the z-score scalar, I can also use min-max scalar, sklearn.preprocessing import min-max scalar, right? Okay, looks like min-max scalar. Yeah, it's slow. I don't know why. Maybe my RAM is totally filled up with all those executions happening in the background. So that's why it is slow. So this is a min-max scalar. So either I can use a min-max scalar or I can use a standard scalar. So in this example, I am using a standard scalar. So standard scalar, I am aliasing it as SC. This is the initialization of the function. sc.fit underscore transform. For every input variable in X, find out the minimum value and the maximum value and try to convert them into zeros to ones. Okay, let me show you like how it actually works. Define a function min-max. I am calling this function as the min-max, and return x minus the minimum of x, and then divided by max of x minus minimum of x. So this is the function that we have written. Okay. Now let's see how this function works. X is equal to 10, 20, 30, 40, 50. So I created a list. So this is a data structure called list in Python. Now on this list, I am going to apply the function min max, and we call that as x, right? So let's pass this x to avoid confusion between the argument name and the argument value. Let's rename the list as a. Now min max of a. Min max is not defined. Oh, it doesn't work on a list. It should be a numpy array. np dot array of this. Look what happened. Um, 10 is the original value. After applying the min-max scaling on it, we got 0 in the place of 10. In place of 20, we got 0.25. In place of 30, we got 0.5. 40, 0.75. Maximum value is 50. We got 1. So this is exactly what we call as the scaling. And here, that's what this inbuilt function also does. So x minus minimum of x divided by max of x minus minimum of x. So we are doing the scaling here, and once we apply the scaling, you could see all those values in very small magnitudes. Now look at the x. How many observations are there? 2666. So this is the number of observations in the training, and the number of columns. The number of columns that we have is 17. So these are our inputs to your neural network, input variables to your neural network. Okay. From TensorFlow.keras.model sequential and TensorFlow.keras.layers import activation and dense. What type of activation we use, and to add the dense layers. From TensorFlow.keras import optimizers, and these optimizers are also are also is going to play a significant role on how we are going to learn. So what this optimizer, the default optimizer that we generally use is called as the stochastic gradient descent. So this is the default optimizer. What happens in stochastic gradient descent? When we are updating the weights of the k plus 1th iteration, we use the weight of the kth iteration minus the learning rate times dou e, the error with respect to dou wi. So this is the default gradient descent optimization. But in some cases, this might be too slow. Why? Think of this optimization like this. Whenever I am here, I am trying to move towards this point. I'm always taking equal size steps. So this is like equal size steps. So because we are taking equal size steps, to reach this, I might need more number of iterations. So this is one of the problems with the stochastic gradient descent. So instead of stochastic gradient descent, I can use some other optimization techniques, which is like momentum added stochastic gradient descent. So what momentum added stochastic gradient descent does to your optimization is, whenever the slope is very steep, so it would take larger steps. As it will become flatter and flatter, the steps will become slow. So that way, it would take lesser number of iterations to reach this, right? So there are so many different types of optimization techniques like SGD, stochastic gradient descent with momentum, ADAM, RMS prop. So when you learn deep learning more in detail, you would learn all of these optimization techniques in detail. What is the difference from stochastic gradient descent to stochastic gradient descent with momentum, Adam, RMS prop, etc. But here I am going to use my optimizer as stochastic gradient descent only, because you guys are not yet aware of the other types of optimization. So I would keep that simple for you. Okay. Now, all those things that are required for us to build our network is ready. So I'm going to show you with very simple steps how we build our network, our multi-layer perceptron. So classifier is equal to sequential. So let me change this classifier name to NN so that it would be consistent and easy for people to whenever they look at it, right? So this is my initialization of the network, sequential. So recall these steps which I have shown you. So sequential, then add layers, add the details of each layer, compile it, and then train it. So these are the steps that I am going to do. Sequential. Now add a dense layer. So this is my first layer, right? So this is my first layer. And in the first hidden layer, I am going to have 17 units. What is 17 units? Units is nothing but the number of neurons you have. And because this is the first layer, I need to mention how many input dimensions are there. So I told you this. For the first hidden layer, we need to mention how many inputs are there. Why it is required? Because it has to initialize those many weights. So that is why for the first hidden layer, we would mention what is the number of inputs. So in this case, my number of inputs is 17 and my neurons are also 17. What is the activation function that you are going to use in the hidden layer? So the activation function that we are going to use in the hidden layer is ReLU. How to initialize the weights? Using a normal distribution, using a uniform distribution. I am using a uniform distribution here. This is the good thing about Python, and especially when you use Jupyter Lab or Jupyter notebooks to build your code. Now, I don't know what are all the arguments this dense function takes. So these are all the arguments that I have mentioned in my dense function. So if you want to know, no need to go for any documentation. So when you use this shift and tab on your machine, it would automatically load what is the functions arguments that this dense takes, and you can see some examples also, right? Units, it takes a positive integer and it is the dimensionality of your output space, etc. So those inbuilt help will try to make decisions of what these values should be. So that's the help that you automatically get. So my first layer is done. My hidden layer is done. See how simple it has become. Yesterday, when I have to build single perceptron, I need to write such a complex code, one function for sigmoid, another function for the derivative of the sigmoid, and then the back prop and forward prop and the back prop. I don't need to do all those things. Simply say my network, add a dense layer to my network. It's like reading English, right? So this is my network. Please add a dense layer to my network, and these are the things that you need to put in the first dense network. Next, the output. There is going to be only one output layer right here. So add one more dense layer. So this is going to be my output layer. Activation is equal to sigmoid, because in the output layer here, we are going with binary classification. So the activation that we are going to use is going to be sigmoid. Kernel initializer. Again, I am going to initialize my weights using a uniform distribution. Okay. Then compile statement. In the compile statement, we need to give all these things. Optimizer. What optimizer that I am going to use? Stochastic gradient descent, because you have just listened to only stochastic gradient descent so far. You don't know other types of optimization techniques. So we stick to stochastic gradient descent. And how to compute the loss? The loss is computed using binary cross entropy. So this is where again the knowledge of machine learning comes into picture. Depending upon your objective, you can choose a lot of different loss functions. Mean squared error is a loss function. Um, RMSE is a loss function. Binary cross entropy is a loss function. When we are building a multi-class classifier, then categorical cross entropy is a loss function, right? So this knowledge of what should be a good loss function given your objective comes directly from your machine learning, right? Metric, what metric that we are going to use to evaluate the model. This is also coming from your machine learning, right? So here, if you remember our first day discussion, when we use a classifier, binary classifier, we try to measure the performance using the metrics like accuracy and error. So here, instead of the error, we are using the metric, which is the accuracy. So those are the details, and my architecture of the neural network is ready. See how simple it is to build a architecture of a multi-layer perceptron using Keras. If we haven't used Keras, if we have to do all of this on your own, we might have taken 1 or 2 full days to do that, because we need to see the derivatives and compute the derivatives, use the backprop for gradients and update the weights. I don't know how much amount of complexity we have to go into in building that. So we do not have to worry about any of that complexity now, right? So in the first dense layer, we have 17 inputs. So total parameters it is going to train is the 306 parameters, including the biases. And in the next layer, there is going to be only one output. So we would be having 18 parameters. So that is including the bias, 17 for the neurons and 1 for the bias. So that's why we are getting 18 here. Now, this is, okay, it's already compiled, right? So I don't need this. So I will take this statement out. Compilation is already done. Now we need to fit. We need to train it. Now nn dot fit. The names has to match. So my network is named as nn. So it has to be nn dot fit. So that's why I wrote this. You just have to remember this very simple flow chart. If you remember this simple 5-line flowchart, you can build a Keras model by yourself. So here we say fit X, which is my input, Y, which is my target, validation data set. I haven't created a validation data set here. So I am using my test data set itself. That's okay. If I had created a validation data set, I would have used a validation data set here. Epochs is equal to 100. So this is the number of iterations. Then the batch size is 32. Stochastic gradient descent will not use all the observations at one go. Instead, it would use a subset of observations at one go. And how many subset of observations that we are going to use at one iteration, I mean, to complete one optimization, that is called as the batch size. Okay, so batch size is equal to 32. Now, when we run this, you can see the training process. It's actually executing pretty fast, right? Each epoch is just like taking a couple of seconds. This is very small data, so it is actually able to execute it faster. We have already completed around 70 epochs, and it would not take much time to complete the 100 epochs. Yeah, it's done. So the accuracy on the 100th epoch is 0.8860. When we actually started it, the accuracy is maybe around 0.85. So over 100 accuracies, sorry, over the 100 epochs, the accuracy changed from 0.85 to 0.88. That's not a significant increase. Maybe we need to train this network even further. We need to train this network even better by increasing the complexity of the architecture, etc. Okay, so nn dot predict. Now we are predicting on the test data set, and it would give you probabilities as your output. So you can see y underscore pred here. I'm going to print all the values for you. These are all the probabilities. For every input, it has generated the probability. And anytime when we have probabilities, what we do, we would try to take the cutoff as 0.5. If the probability is greater than 0.5, we will consider that prediction into 1. Otherwise, we will consider that prediction into 0. So this is now this rule here, if ypred is greater than 0.5, then it would be given as 1. Otherwise, it would be given as 0. Now let's compare how good is our predictions. So we are going to make a comparison between our predictions and the actual outputs of your test data set. So that's called the confusion matrix. So this is your confusion matrix and accuracy score. The accuracy score that we have got is only 0.89. So this is after just building one simple neural network, a multi-layer perceptron, and training it for just like one iteration. And to get the best out of it, we need to train it. We need to find out all the optimistic parameters through which we can generate our desired output from the inputs. Let's say we want to add one more hidden layer. Then we would simply let's activate one more hidden layer here and put that, copy paste it. And here I don't need input dimension. Why? This is not connected directly to your input layer. So I'm not going to add this. I'm going to just add number of units 8, and my activation is still going to be ReLU. Kernel initializer is uniform. Now what I did change to my neural network is like this. So inputs are 17, x1 all the way up to x17, and my hidden layer 1 has 17 neurons. So this is your 17 neurons. Now my hidden layer 2 has 8 neurons. So this is my hidden layer 2, and my output, which is going to be 2. So adding a hidden layer to your network is just like adding one single line of code to your architecture, to your ANN architecture in Keras, right? So with one single line of code, we have increased the complexity of our neural network. Now you can see here, the first dense layer, number of inputs is 17, so 306 parameters. Second hidden layer, 8 in 8 neurons, so 144 parameters. And the last layer is going to be having 9. And let's retrain this. Now it might take a little more time for each iteration because the complexity of our neural network has increased, and maybe even the training would need little more epochs than before, because it was actually not learning much. We might not get a better result than what we have seen before, but this is where you need to spend time. This is the parameter optimization that I am talking about, hyperparameter tuning that I am talking about. Where we spend a lot of time as a AI developer is to finding those right set of parameters to get your desired output. Writing these programs is like a cakewalk. anybody would be able to just do it, right? How writing these 4 lines of code, understanding each of these parameters, finding out these values is not big deal. But trying to get the best network that can generate your desired output is a time-taking process. So this is where we spend a lot of iterations to get that desired output. This is very simple data set. When we look at some of the complex data sets, especially when we are training them using images, etc., it would be even more complex. It would be the network architecture would be even more complex, and then the training process would be complex. Now it hardly took a couple of minutes, actually not even a couple of minutes, a little more than a minute to complete these 100 iterations. But when you feed a huge volume of data and try to train it on X number of iterations, huge number of iterations, this whole training process might even go into hours. So that is where we have to think right parameters and put the right parameters so that you do not waste a lot of your training resources. Once you submit this program, it takes 5 hours for training. So that's what you are going to do. You have nothing to do. It is just going to run in the background, and you probably spend all that time somewhere else, right? Now if you don't take at least a good guess at what is the right set of parameters, you might do this 100 iterations, 100 into 5 hours, like 500 hours, and you still not be able to figure out what should be the right hyperparameters for your network. So that knowledge of how all these neural networks work, what each parameter does to your network, is critical when we have to train this. That's why we are learning all those concepts behind the scenes. What is stochastic gradient descent? Why is it not good? Why we can go with some other learning parameter, right? Now I have changed my network. Sorry, I have changed my optimizer to Adam. You might not know what Adam is, how it actually works, because it might take a lot of time for me to explain that. But from stochastic gradient descent, we changed that to Adam. Now I am training my network with Adam, and let's see if Adam is able to perform a better job than what we have seen before on the test data set. Look at 84 accuracy, 84 epoch, the accuracy is 0.92. Previously, when I was using stochastic gradient descent, it was just 0.88. And let's compare the predictions now. Now, when you go ahead and try to build the confusion matrix and the accuracy score, look at the accuracy score. Wow, 0.929. From 0.88, it jumped to 0.99. And look at the confusion matrix also. It is much better than in its previous case. Okay. So this is how you you train a neural network. You have to decide your architecture. You have to decide each and every parameter in your architecture and build that architecture, compile it, train it by feeding the data in, and you do this repeatedly until you are satisfied with the results. This process is exactly what we call as learning, and all of this training happens through neural networks, which can find out very complex interpretations, which can find out very complex patterns among your data in general other machine learning algorithms are not capable of. And that's why AI or deep learning based ones are so powerful and are game changers in this industry of AI. Okay, I think that's all I have. I'm open for questions now.